information concerning his resume there. So he was the chair of the Airbus Group share, and is also leading now an industrial chair with ESI Group on advanced modeling and simulation of material, processes, and structures. He received many scientific awards, but let me point out that he was one of the ESAFORM Award fellow. He's author of a lot of paper, more of 400 papers in peer review, and of course contribution to many conferences. And he's the president of French Association of Mechanics, used to be the president of French Association of Computational Mechanics. So he's a really renowned scientist in France and in the world. He's the editor of many journals. Maybe I should point out, he's the editor-in-chief for International Journal of Material Forming, that is the journal of ESAFORM, and also director of the Descartes project, that is more than 35 million euros. Okay, so I must add that Paco is a very active member and friend of ESAFORM. He used to be one of the members of the board. He is the editor-in-chief of the journal, and he organized one of the conference. So I leave you the floor, Paco.
Thank you very much.
I'm very happy to welcome you.
Thank you very much, Katia. Thanks, obviously, organizers, for inviting me. So I will try to share my screen, and I need only that you confirm that you can see my screen, and I don't understand that, but probably if you can, if you have my screen. So this is the title of my presentation today, is about digital twins, because they are helping us to make a better engineering. And the two main objectives of engineering, this is the same for all you. We need to design and we need to operate the things that we design and that now are in service. So this is a very large topic, and I would like to make emphasis in some technologies, and obviously I will try, even if this could be applied in many domains, going to the domain of manufacturing and material forming. So first of all, there are few introductory slides in order to be all us in the same page. The first one concerns the level of digitalization of an object. As you can see, we have on the left something that is in design. The object does not exist. There is no real data coming from this asset because the asset, we are in the designing phase. And you can see that there is something on the right that is in operation. This means the asset is there, and now we can continue the digitalization. If we are on the left and the design, the first one is when you are trying to make the geometry of the asset. You are creating an object, you are creating a car, you are creating something. So there is a designer that is creating the aspect, the geometrical aspect of this asset. And this is very good. This could be a digital twin in the sense, it's a twin for the object of interest, that in that case is the geometry, and it's digital because this is in our computer. So if you want to call this CAD, you prefer to call it a digital twin. Obviously, for the design stage, this is a digital twin. Obviously, this is not the end of the design because we need also to ensure that this design is working correctly. And for that, we need to emulate its functioning. And for that, you know very well, we have all the finite element simulations, for example, that allow us to put physics into the geometry. And as soon as you put physics into the geometry, you could now check if the operation is good, if you can manufacture this product, and if this product is operating correctly in the future. So in the center, you have the classical simulator tools. And this is also a digital twin in the sense it's a twin. It's representing a reality, and it's digital because it's living in your computer. So for me, all these are also digital twins, but you need to specify in what sense. On the left, on the aspect, on the geometry, in the middle, with respect to the expected physics. Expected because this object is not manufactured now, and it does not exist now. And on the right, we can assume that the object exists, we just manufacture it, or we are manufacturing it. It depends if we are in material forming or in operation. And obviously, at this moment, we have a replica of it in my computer. There is the real object, and there are data that is coming from the object to the computer. We call it monitoring. And data moving from the computer to the asset, we could call it control. So finally, very easy, this third digital twin in operation, there are three components: the asset, the model in the computer, and data that is moving from one side to another. So we are focusing in the last one because it's the one that is the most challenging in the sense we need to predict very, very fast in order to take the right decisions. And you can see on the right in this slide, the digital twin is based on the best available multi-physics, multi-scale, and probabilistic computational model that is replicating your system, and sensor data, as I mentioned before, that is making possible monitoring and control. And what we expect on this digital twin? We expect to mirror and predict. The prediction is the science of engineers, predicting the functioning and the performances all along the life cycle is possible of the associated physical asset. And obviously, it's better that we make a dialogue with a model in my computer than trying to make a dialogue with the asset itself, because in my computer, everything is inside. In the reality, there are few sensors, and the information that I can collect is very limited. So this is the interest of having something digital that is replicating or emulating the physical reality. Now, there is a question that we need to solve. We need a model. The model is in my computer, everybody agrees, and is the replica of the reality. Now, there are two paradigms. There is the paradigm coming from the past, the physics. The model is based in the law of physics, or the one that is in the right, that is the one that is more recent, that is, we could create a model as soon as there is data by using artificial intelligence and machine learning. So now the question is, I choose the one of the past, or I choose the one of the right, the one of the more recent based on data, because this is new, because this is very promising, and because this is very timely. The question is, I don't know your opinion, we could discuss at the end, but obviously making everything based on physics is a little bit delicate, because reality is reality. Our models are our models. When we model by using physics, we simplify. And when you simplify a little bit, or you know only imperfectly some of the parameters that are involved in the model, this means that when you are moving far in space or time from the present, there are bias, there are deviations that will appear. And you know very well, people predict of weather, a fantastic weather for the weekend, and many weekends finally it's raining. So physics, very, very good, but obviously physics or models are models, reality is a little bit more complex. On the other side, we could decide, okay, now in order to make better, we are making something only based on data. The problem is in data, in many applications like Google, it's not so expensive. But in engineering, data means you need to put a device that in general is very expensive. You need specific machines in order to perform that. You are collecting data that you need to store, to communicate, to transfer, that you need to manipulate, and at the end of the day, you need to construct a model. And obviously, after constructing this model, you are not sure if it's correct or not. This is the problem of explainability when you are making model by using artificial intelligence. And it's very well known, you cannot extrapolate because extrapolation is very dangerous in all the branches of physics and mathematics. So finally, only data is very expensive and almost unrealistic in engineering. Only physics is the engineering of the past and is a little bit delicate because when the systems are very large, we have some problems to well represent them. So now the question is, maybe there is a third option that is making something in between that we call it hybrid, and is the one in which I will focus in few minutes. Obviously, there are data. We need to be clear. We need to collect the right data. The right data means the one that you need in order to make predictions. No more, no less. You need to decide at what locations making the measurements and at what time take the data, make the measurements. So this means we need to transform and we need to replace this big data paradigm, but something that is more in the philosophy of engineering, only useful data. The right data at the right place at the right time. Second, we are trying to make design, and an optimal design is the one that allows reducing operation cost while meet performances. Performances are very important. We are making designs in order to meet performances. And when we are speaking about operation obviously aims at maximizing the efficiency. And for that, you need to make predictions as accurate as possible, as fast as possible, as explainable as possible, and you need to operate in very large systems in general and make attention with few data in general because there are many technological difficulties and also the cost related to the data acquisition. And for that, we are proposing, and this is the main aim of my presentation, creating something that is conciliating both paradigms. We are using physics, and when the physics is not enough, we are trying to use data in order to enrich the physics. So in all my presentation, hybrid paradigm means we continue working with the models that we know for centuries. We continue working with physics and applying physics. But obviously, if one day there is a gap between our predictions and the reality that we observe, we are using artificial intelligence, we are using the data, we are using this deviation that I will call later ignorance, in order to model by using machine learning the ignorance as the part of the reality that is in the reality but is not in your models. So finally, AI, yes, welcome, but only in order to enrich or to correct our knowledge. Is not there in order to rediscover all the things that we know very well nowadays. And this is explained in this synthesis slide, in which you have on the left the virtual world. There is plenty of physics, there are many models, and there is many software that is ready. The problem is you need time in order to process. You need big computers. When the system is very complex, there is a lot of variability, one uncertainty. The predictions and the reality does not correspond. On the right, you have the digital world. You have or not a model, there is no problem, but you have data. For example, you have many inputs, F, and many outputs, U. In mechanics, F is for the force, and U is for the displacement. And you have many data that you collect in your life. And now, if you use machine learning, you can learn the model that relates the input F with the output U. This is machine learning. You don't need physics. The only thing that you need is the right data in order to elaborate the right model. What is the problem of this paradigm? That, as I just mentioned before, the data has a cost and is not negligible. You need to decide which data, where and when, and artificial intelligence cannot help with this. Is something that you need to put inside with your knowledge, natural knowledge. And as I explained before, extrapolation and explanation is the main issue. So finally, we are looking something in between. And in between both, in between the virtual and the digital world, you find something that we call informed or that we call augmented. It's not very different. It's the same idea. In the informed, you are creating a model. If you introduce the input X, as you can see in this small equation, you would like to obtain the response that is U. And obviously, you would like to create this model, X to U, but you know something about U. You know, for example, that this U, that could be, for example, the temperature field, should satisfy more or less the heat equation. And in that case, you can construct off of X from data, but you enforce that you know something about the physics, because you know that this physics, for example, is fulfilling something like the heat equation or the balance of energy or the entropy production or thermodynamics that you cannot violate. So all the information that you have could be introduced as a constraint when you are learning from data the relation between the input X and the output U. And in the augmented is more or less the same idea, but a little bit different. The reality is the one that we are looking for, the model that relates X with U, but now you have something also, you know something about the physics, and you have a prediction based on physics that I call UP, P from physics, that you know the relation for many years that produce this U depending on X. And now, obviously, if the reality OX that appears in the left is not in agreement with your model UPX, this means there is an ignorance. There is something that I need to add to the component based on physics in order to reproduce the reality. And as you can see, I call it UDX. This is the model that I discovered from data. The artificial intelligence and the machine learning is only when I'm constructing this UD, because for the UP, there are centuries of science. And obviously, by using one or the other, you can reduce the amount of data, you can move faster, because there is a lot of knowledge that exists and you put inside, and you can explain. In informed, you can explain that your solution is not very far from the things that you know, and in the augmented, you can explain that at least most of the solution, based on the physics, is very well known, and today is the basis of engineering, and we are certifying engineering thanks to this UP. So finally, it's a nice alliance between the world of the past on the left and the world of the future on the right. And this is very comfortable, in particular, for engineers and for industry. This is the main advantage of speaking about informed or augmented learning. Informed, I just mentioned this, and this is an image of a colleague, Elias Cueto, that is also very well known in the community of ESAFORM, in which we are learning the behavior of a fluid. And when we are learning the behavior of a fluid from the data, from something that we observe, that is the movement of a fluid in a glass, we try to enforce that this physics should be in agreement with thermodynamics. This means we need to conserve the energy and we need to produce entropy because there is the viscosity that is giving an irreversibility to your dynamics. So we are learning the behavior of a fluid, and we are informing in the learning that we need to satisfy the thermodynamics and the state of the system, as you can see on the left, on the bottom, depends on a Hamiltonian. This is the part coming from the conservation with the gradient of the free energy, and a part that is dissipating, this is the matrix M, with the correspondent gradient or potential, that is the gradient of the entropy. And when you are learning with this is a short video that is now theoretically applying on the right. You can see we can introduce a synthetic fluid. We are trying to learn. This could be synthetic or this could be real fluids in which you observe the free surface. We can consider different behaviors, linear, non-linear, depending on the internal variables, depending on the history. And obviously, we are learning in the right manifold by using the right physics. And the most important point is, as soon as you learn, you can see the empty glass in the middle. Now the fluid, we are introducing the fluid inside, and the movement of the fluid we can compare with the reality is very, very close, and we can ensure that this movement is in agreement with the thermodynamical principles, because we inform in the learning that we would like to feel this behavior. Now, if we move to the hybrid, obviously, the interest of the hybrid, I will try to comment this in this slide, is you can reduce a lot the amount of data that you need in order to learn the system. Imagine a real system, like on the left on the top, in which you have a real behavior. This is the continuous line, and you have a model that is the discontinuous red line. We can conclude that our model is not so bad, but it's not perfect, because we can see that when we are moving far from the present, the gap is increasing. So obviously, if your model, you are not happy, you could take the decision of neglecting the model and trying to obtain the information by using only data. And we are moving to the image on the left on the bottom. You make a measurements at 0, at 02, 04, 06, 08, 1. And if our sensor is good enough, accurate enough, you obtain something that is very close to the reality. The problem is, and in between, oh my God, in between, I never make a measurement. The only thing that I can is make a straight line. And you can see, if you make this, the tendency is quite good, but finally the solution is not better than the one that you compute by only using physics. For that reason, people in data science prefer speaking about big data, because if you make a million of measurements, obviously, with a million of measurements, you are approaching the red curve. But by using only 6, like in this case, your solution is very bad. But the problem is, in engineering, data is very expensive, and making 1 million measurements in 1 million points, this is very, very unreasonable. And for that reason, we decide to make the hybrid approach, that is the one on the right, in which you can see, when we represent the ignorance, the deviation between the real and the model, that is the difference between the continuous and discontinuous red lines, you obtain something that is the blue one. That is almost linear. Why is almost linear? This is mathematics. When you have a very good model, you are not so far from the reality. And when something is small, this means if you make a Taylor development, you know very well that the first term, that is the linear, is the most important, and the quadratic, etc., you can neglect. So this is the interest of having a very good model. If you have a very good model, the deviation is very small. And something that is very small, when you make a Taylor development, is quite linear. And when something is quite linear, few points are enough in order to approximate it. So finally, the main message is use a very good model and few data, and this is enough in order to have a very nice approximation. And now, this is the most important slide, that is introducing the concept of hybrid twin, in the sense you have your real asset, your real machine, your real process, your real structure on the right. You have a model on the left, multiphysics, thermal science, computational fluid dynamics, solid mechanics, all the things that you want. The model can be simulated, oh yes, and in the physical asset you can collect some data in the right place, in the right moment, you know very well this. And if you are collecting data and you are making simulations, sometimes you should compare if the things that you measure are the same than the things that you simulate. This is the minus that appears in this circle, and this means If this subtraction is 0, this means your model is perfect and you can continue to make engineering. But if the difference is not 0, this means there is something in the reality that is not in your model, something that we call ignorance. And when you detect this ignorance, you are tempted to use machine learning to construct the model of the ignorance. So finally, we are using machine learning where? We are using machine learning in order to accelerate, to compress the finite element simulation in something that we call model order reduction. Model order reduction is a regression in order to describe all the simulations that you perform offline. And we are using also machine learning, the same technology, in order to extract, in order to learn, in order to obtain a model of the deviation between reality and your simulations that we call the ignorance model. And as soon as you have both the surrogate and the model of the ignorance, you add both contributions and you have the hybrid twin just in the bottom that express the state of a system evolving time, because there is a very well-known physics that now is real time because you apply model order reduction plus the model that is coming from the ignorance that we just model by using machine learning based on the deviation that we notice between the data that we collected and the simulations that we perform. And this last equation in the bottom, this is the hybrid twin in the sense we are simulating in real time very accurately. And this means we could make very nice predictions, and with very nice predictions, theoretically, we can make very nice engineering. So for my model order reduction, I have no time to move in, but there are the regressions, sometimes polynomial regressions, something that is richer, but you need to regularize in order to have something complex by using few data. If you are interested in polynomial regularized regressions, how to make something very complex with few data, this is mathematics. There is a least square that the final ill-post problem, because there are many richness with respect to the number of data, and by adding a regularization, you can obtain something that is very complex with very few data. And if you prefer, because you have a lot of data, don't hesitate. If you have a lot of data, use something like neural networks that assimilating or replicating the functioning of our brain, is manipulating neurons, is computing the weights in the connection between neurons, and adjusting the bias in each one of the neurons in order to put in relation the input data that you know and the output data that you know. And as soon as you compute all the weights and all the bias, you have a model, and from now, if you introduce the input, you obtain in real time the output. So this is neural networks, very popular today because it's very transparent, because there is a theorem that is the universal approximation theorem that establishes that any nonlinear function can be approximated by a very large layer, layer of neurons, and like you can use it in order to solve all the problems that you want. This means approximating any kind of nonlinear systems. So some examples in order to show how it runs. Maybe in this image you have something on the left. This is welding. There are many parameters in the welding. We create a surrogate based in model order reduction and a commercial software. And now as soon as you construct this meta model, this surrogate, you can change the different parameters, and you can evaluate in almost real time what is the effect of the different parameters into the solution. In this case, is the temperature field, but this could be the metallurgy, the plastic deformations, the residual stresses, all the things that you want. So this is one example in order to prove some design of experiments, some data that you can generate. This is not experimental, it's generated by a high fidelity software, and you create a regression in order to speed up simulation. The solver takes a lot of time. This surrogate is giving you a response in almost real time. So this is the advantages of this kind of meta models in order to speed the simulations. Now we move to another case on the right. It's a case of multi-step stamping in which there are many operations, 1, 2, 3, 4, 5, 6, 7, 8. There are also the transfer from one to the other. Each one of the process has until 4 parameters, and this means at the end of the day, when you are making all the operations, you have about 28 parameters, and each one of each parameters in each one of these stages has an impact on the final solution. Here we are looking for the residual distortion or for the residual stresses or plastic deformation in some of the points. So this is the tool. I try to accelerate a little bit, but you can see we can modify these small buttons that appears here in order to change the conditions, and in all the cases we can evaluate, as you can see at the end, what is the final part with the dependency on all the parameters that we introduce in the system. So not time to move to many other operations, but this can apply in a very systematic way in many domains. We can use also in order to, for example, in composite forming, by using this kind of tools, you could decide, depending on the properties of matrix, depending on the properties of fiber, depending on the type of composite, you can use it in order to evaluate in almost real time, in the linear and non-linear case, what is the homogenized behavior. And as soon as this kind of system, you put different conditions and in real time you have your homogenized behavior, now this means you can introduce this in each Gauss point when you are making a simulation, for example, by using a UMAT, and this means in real time is like the finite element square, but the main advantage is, in that case, you are particularizing the solution in each Gauss point in almost real time. On the left is something that is perfectly elastic. On the right, you have something that is perfectly inelastic, in which obviously we are approximating the dissipation and the free energy when we are putting all this in a thermomechanical setting. But finally, the important point is you can use this kind of parametric solutions in order to homogenize, and after we can use a standard structural mechanics simulators in order to make the global problem. So micro based on AI and macro based on the standard equilibrium that we have in structural mechanics. There are many options also to create, because until now I use only physics. This means creating machine learning from the finite element simulations. Obviously, we could also using data, because at a certain point by using data I need to create a model, and there are many technologies to create models from data. Almost all the people connected today in the webinar, they are creating models based on data, and for that you can take any option that exists in all the libraries in PyTorch and TensorFlow, etc. Today we have a collection, a panoply of technologies that you can apply, and in general, when the amount of data is large enough, all of them are given very, very nice results, and this is something that today is quite mature, the fact of learning a model from a data. Some examples that we applied in the past, for example, when we are making a spot weld and we would like to behavior of each spot weld when there is a crash in a car. Obviously, the spot weld is a 3D simulation that you need to move from elasticity, plasticity, damage, and fracture. This is extremely expensive because there are thousands of spot welds in the car, and we decide, as I just mentioned before, to create a surrogate of the spot weld such that when I know the force that we are applying, it allows to me to compute the state. And this means when this is possible, each spot weld is replaced by this surrogate, but this machine learning based because this was a neural network. And finally, we can compute at the level of the spot weld or at the level of the car the behavior when we are applying different kind of loadings. So this is the important point: local machine learning, global structural mechanics. But the important point in nonlinear mechanics, you know very well, that is evaluating the nonlinearities. The nonlinearity, the difficulty is nonlinear. The advantage is local. And because nonlinearities are difficult, but are local, we can create a local model in order to evaluate almost in real time the behavior of something that is nonlinear but is local. And after, the equilibrium obviously is global but is linear. So this is the idea. The global is linear, the local is nonlinear, so we put machine learning in order to compute the local. We apply this also in riveting, and this is a nice example in which even when you have a very complex model that you are simulating, there are many parameters, and everybody knows that calibrating a model and simulating a model, this is very tedious. There is something that we can obtain with a machine, that is the force displacement curve. And in a certain way, this curve depends on all the parameters in the real behavior of our material. So finally, as depending on the process, we have a final configuration. And in this final configuration, we can obtain some parameters that are quantifying the quality of the riveting. The idea was taking this curve that are machine, is something that we can observe in the machine. We could use an autoencoder in order to move in their latent space and remove all the correlations. And we create a model in between the curves that we measure and the quality parameters as an output. And this means today we can, from a curve, determine is the riveting has the right quality or not. And almost in real time, without the need of simulating, because we simulate a lot, but only for training the relation between curve to quality. Curve is something that we observe, and quality is something that I don't observe because are things that I should cut in order to obtain the response. But obviously, because the learning, we can assume that we have a very nice approximation. In the same way, in SMC, sheet metal compounds, molding compounds, we can, for a given mold, determine what is the position and what is the shape of the preform, the pre-charge, in order, when I squeeze it, when I compress it, at the end, we reach the target geometry. And this is something that from some simulations and machine learning, we could create something that could be even deployed in the machine. This is your mold. Please take the preform, place in this point with this shape. This means the orientation, the shape, and when you compress, the material will reach the border of the mold almost simultaneously. And finally, there are no material losses, and you are reducing as much as possible the load and the energy that you need to apply in the process. The same for polymer extrusion. When we are extruding a polymer, there is a big difference because the die swelling between the die that we expect and the geometry of the real extruded part. And we decide to create a model between the relation between the final extruded profile and the shape of the die. And this means today, if you are interested in obtaining a very good profile, we can determine in real time what is the shape of the die in order to be sure that there is a perfect agreement between both. This is something that we published a few months ago in our journal, the Journal of EFRAFORM, with Goodyear. Is a public work, but this is the use of this kind of neural networks in order to connect die with final geometry. And obviously in composite we can use in order to simulate in almost real time. Please provide me a microstructure. You can see here, there are voids, there are fibers, there are matrix. and after learning, and there are never two microstructures that are the same. In the composite, obviously the fibers are not always in the same place, and the porosity is not always in the same place. But the point is, when using a very nice model, as soon as you provide me a totally different microstructure, but I learn very well my model, in real time I can produce, which is the temperature field associated to this. So this is online monitoring, online prediction, obviously by training a model that in that case is quite complex because there is a microstructure that is too or very, very rich. And now we could put both together. This is the end of the presentation. And I will give you some ideas about how we put together this model that I just explained. By using neural networks, input and output data, we can create a model. And the model order reduction that was, I make plenty of expensive simulations and I will compress all these simulations, creating a surrogate model that I prefer calling it model order reduction or not artificial intelligence, because there is not intelligence, there is no learning. We are only compressing the finite element simulation. But the important point is, at a certain moment, we need to put both words together in order to create this very nice, very fast, and a very accurate approximation of our reality. A first example, and after I show a couple more, and this will be the end of my presentation. This is RTM in order to give some ideas. This is the filling of a mold, and we put this obstacle that is in black in order to have a visual representation. Obviously, everything is not unknown. We know for many years that the domain in which the fluid is, we call it omega. A point in it, I call it x. We know that there is a pressure field, oh yes, and we call it P of x in classical mechanics. We know because there is a gradient of the pressure, there is a velocity, and the velocity is called V of x. And there are many things coming from the last century in which we are relating the velocity with the gradient of pressure. This is called the Darcy's law. And we know that the fluid cannot disappear. This means in the region, in the fluid domain, the divergence of the velocity field is zero. And when you put this V into the continuity equation, you obtain something that is an elliptic problem that we are solving. So this is very nice because with this we can simulate problems. And this is one case in which you can see everything is going well. And this means that the simulation and experiments are almost perfect. And you can see that until this point at the beginning, everything was going very well. So no need of artificial intelligence. We can use model order reduction in order to solve the Darcy's equations in a very effective way. But the problem is there is something in this system that my model ignores. My model ignores that when we are very close of the border, the permeability decreases. And this is not in my model. I never train my model based on mathematics, based on physics. And finally, the experiments are on the left, the reality, the simulation is on the right. And you can see that at a certain moment, there is something in the reality that is not in my model. My model ignores that there is a change of the permeability, and in the reality, there is a change of permeability. So this means my model was quite good at the beginning, but at the end, my part was not satisfactory. So what is the idea of the hybrid twin? We start with the physics. But as soon as we detect that there is something in the observation that is not in my model, we create online, in real time, a model of the deviation, a model of the ignorance. And from now, my prediction is the one that is coming from the model that is not good enough, plus the model of the ignorance that we create, and we are updating continuously in order to be sure that we are emulating, we are replicating the reality. And this is the simulation in this slide. At the beginning, no hybrid twin, only physics and model order reduction. We are simulating the reality. Until now, everything is going quite well. And at a certain moment, the deviation appears, and my model in real time adapts by adding the model of the ignorance and as soon as it understands that there is a permeability that change, we can simulate and it's working well until the end. So this is the idea, it's quite simple. Is as soon as there is a deviation, as soon as the physics, your model is not enough, we can make two things: spending years in order to make better by using physics, or be pragmatic. Okay, I accept my model is not stupid, but it's not enough. As soon as I can identify the ignorance in my model, at this moment we could enrich it in order to obtain better solutions. This is one case, and I will show both of them and we will finish. This is one in casting. We can observe that we measure the temperatures. We make the simulation by using a state-of-the-art simulation software. And when we compare in these sensors the real temperature that we measure and the one that is coming from the numerical simulation, you can see there are deviations, not too much, it's in the order of 10 degrees, but there are deviations between the simulated process and the observed one. And now the question is, could we try to improve the model in order to reduce this gap between the experiment and the simulation? And you know now, the idea is take these curves, and we need to create a model of the difference, a model of the gap. This gap is deterministic. It's there because probably there are a transfer coefficient that we don't fit correctly. The model was not very well calibrated because there is something in the reality that was not like in the experiments. And for all these reasons, there is a deviation, but the deviation is deterministic. If the deviation is deterministic, we could use a machine learning technology in order to compute the model of these deviations. And this means if I compute this model, the only thing that I need is I simulate, I add the model of the deviation, and I will have something that will be very, very accurate. And finally, we are using the model because I like the models. I understand the model. I understand the model because we are using fluid mechanics, we are using thermal science, we are using all the things that we know for centuries. And obviously, when making the model of the ignorance, the deviation, is not so evident because this model is like a black box and we cannot control it. And this is in order to prove, after correction, the experimental one minus the model and the correction. You can see here that now the error, maximum error, is about 0.3 degrees. And this is the good news in the sense you can correct in order to make best predictions. We have not a best model because I cannot explain why I add a correction. But at least if you are interested in predicting the solution, because depending on this solution, there are many things that could occur. The only thing that I could guarantee is, even if I don't understand why I correct the model, why I enrich the model, and what is the physics hidden in my initial model, the only thing that I can ensure you is the predictions that you are obtaining are better than the ones that you obtain by using only numerics, only physics. And obviously, not many data is needed, in the order of few, and obviously this could be impossible also if you are interested in modeling all the process by using only data. It's absolutely impossible, but by using only 5, 6, or 7 sensors, you determine the temperature field in the part, in the mold, and with a very good accuracy. This is absolutely impossible, but by using physics and correcting it by using few data, this could be enough in order to have not a better model. I don't know the model because I don't know what is the physics that is hidden, but at least I have a very good prediction. And if you are interested in the prediction, this is perfect. If you are interested in the model, this is not enough, because this allows to obtain something that is very accurate, but you don't know why now you need to correct what is the physics that is hidden. And there is another one that is about stamping. We have very nice model based on physics. We can put some sensors in order to determine, for example, the thickness of the part, because obviously there are reductions depending on the plastic deformation. We have a model that is based on physics. This is nothing. This is modifying the parameters that you can modify, like some material parameters, the friction coefficients, etc. And you create a model that is coming from the physics. This is based on high fidelity simulation of any commercial software. Or after you take the data that you simulate, you make few measurements. In that case was 6 points that you place in the right place because you know that are places in which something is occurring. And with that, you make a data completion. And after you create the model of the ignorance, this is the model of the ignorance. And when you add the model based on physics and the model of the ignorance, at the end, you have something that you can see here, in which by changing the different parameters, you can evaluate the different fields. And this is much more accurate than obviously using only physics, but obviously infinitely more accurate than by using only 8 data, because by using only 8 data, you cannot predict things when you are far from the points in which you are making the measurement. So this is the main idea, and this is the main concept that we have in this concept of digital twin. So I propose stopping here, because there is another part in my presentation that is for the future, but not for today, because if not, the presentation is very large. And this is only in order to show you that today, that all these technologies are quite mature, the great challenge and the enormous opportunity for all the community of structural mechanics, forming process, computational mechanics, is making something with something that is very timely, that is called generative design. Generative design is generative AI. Everybody is speaking about ChatGPT. Why? Because until now AI allow us, in my presentation before, making faster and making better. It's not so bad, eh? Making faster and making better is very good. On the contrary, I'm very interested in making different. And making different, this is another thing. And this another thing, the making different, is using generative AI. When you are using ChatGPT, you put a question and ChatGPT provides you something new, a new paragraph that never before this was written, but is proposing you something different, that is in order to respond, in order to provide an answer to request. And this is not only making faster and making better, this is making different. And this is essential in design. In operation, hybrid twin is perfect. Digital twin is perfect for operation. But for design, we need to move outside our comfort zone. We need to produce things that never exist before. And for that, artificial intelligence should be different. It's not only training, it's more than training, because when you are training, you are obtaining the things that you train. Here we would like to move to things that you never see before. And this is all the things related to generative AI, to generative design. In the case of engineering, this is very timely. And this means we could explore millions of new designs, and you could optimize, or you can choose the best inside in order to maximize the performances, or in order to maximize some properties in it. So the future is not digital twins. This is mature today. Is even not more the research, the fundamental research. We are moving, obviously, and we need to implement this in industry. There are many things to accomplish. Everything is not finished. But now the new generation is, we need to create the ChatGPT of engineering. And it's not a ChatGPT based on LLM, large language models. It's a ChatGPT that is providing you residual stresses, is providing you fields, maximum temperatures. So it's something different. It's not only language, it's something that is generating hybrid twins. So generating hybrid twins related to many designs, facilitating that you take the right geometry, and in real time you know the performances that are associated to them. This is the new opportunity. I have a presentation for that. It will be in my slides, but I have no time in order to speak about all these kind of things, but maybe this will be for another opportunity. Thank you very much.
Thank you very much, Paco. And I really like to thank you for this very interesting, and maybe we can agree that will be maybe a next webinar, maybe next year, about generative design. What do you think?
Excellent, excellent.
Okay, so you have a lot of things to say, and but we still have some time for questions because we do have a huge constraint. Okay, we need to finish in 15 minutes.
Yeah.
So I will ask in the assembly for the participants, if you have any question, please go on. Or do we have Antonio? I see you switch on your camera.
Yeah.
Hello, Antonio.
Hi, Paco. Nice presentation. It was really challenges, all these new technologies. I have a question concerning KPIs, metrics to measure our digital twin, and particularly in operation. Okay, we are very used to measure, for example, the quality of our models, our simulations, but when we are doing on real time, this makes difference, isn't it? And so, what are the metrics that you use to evaluate if your digital twin is really of good quality?
Yeah.
How you do it?
The digital twin, as you remember, they have two components. The first one is based on physics, and this means you use the best finite element simulation and you verify convergence, you verify the error that we have, you make all the classical things that we know for decades. Now there is the other part that is more complex, because this means you have data and now you need to construct a model. The problem is when we move there, we are in the kingdom of machine learning. What means this? The only possibility is you have data. We have 2 times the number of data that we need in order to construct the model, because there is the half that we use to construct the model, and there is the other half that we are using to test the model. There is no other possibility. This is machine learning, you know very well. You separate two sets, the set in which you learn, the set in which you test. And obviously, now the big question for Antonio, that is a very good question, is even if the test is good, can we certify that even if in the test points your solution is not so bad, this means that in all the other points the solution will be good? And Antonio, the question is, obviously, we don't know, there is the risk, but there is only one point that is very favorable for us, is we are using physics. And I explained before, the ignorance is small.
Yeah.
I made my best in order to the ignorance is very small. This means if you have an error in the prediction, you have an error in the evaluation of the error, but not in the evaluation of the most part of the solution in the digital twin, that is physics. For that reason, it's much less risky commit an error in the model of the error that commit an error in the model that is providing you the 95% or the 90% of the solution. So obviously, there is not possibility to evaluate today. There are many people working today in certification, explainability, etc. of the machine learning. In our case, will be always difficult, because these guys with a lot of data, they will arrive. But in engineering, you agree with me, Antonio, we measure only the things that we can, not the things that we want. Sometimes we measure only the things that I can, in the points that I can, even if are not the things that I would like to measure in the points that I would like to measure. So this means we are accumulating a lot of difficulties, and this is an important point for this hybrid twin. Please keep all your physics and make a little bit of machine learning to correct, to enrich. Because I agree with you, Antonio, this part today and for engineering is very risky.
Yeah, really. It's true. And you know, I also think that, for example, we are using the model, and at the end or at the middle of some operation, or we are seeing that sometimes we need to retrain the model again. And my question is again, what should be the KPI for how we know that now it's time for retraining? No, we need to wait some time. How is really tough when you do it real time?
I think the compromise there is, you have a budget.
Yeah.
And this budget is providing you the number of points that you can put in the system, the
Yeah.
number of observations, the number of sensors. When, with the number of sensors that you have, you don't arrive to predict the future. Because at the beginning, even only the model is going well. When you are in the elastic part, imagine, the model is enough. When there is something that is coming, well, at the beginning, with few points, you are trying to learn the process that is coming. But at a certain moment, the things change a lot. The model that you pre-train is not able to continue, and the metric is, with respect to quantity of interest, or with respect an L2 norm related to a field, I don't know, it depends on the application, you need to retrain, and obviously, to retrain and be effective, please use transfer learning. Transfer learning is, I'm trying to enrich the pre-trained model and not create a model from scratch. So this is something that I call continuous learning. Continuous learning is, I predict, next step, I check if it's good, or the error that I assume with respect to a quantity of interest is smaller than a threshold value, I continue. If not, I need to enrich the model that we are continuously training.
Okay, I just have a question. You said for you, digital twin is mature. I understand from the research point of view, but do you have any idea in industry how many digital twins are already used?
When I explain the digital twin is mature, obviously is at from the research point of view. From the implementation today in industry, at least the industries that I know, for the one that I'm working, some of the examples I present to you in the presentation, they are today, they are making use of that. Making use. Making use means probably they are validating, not using in production. They are validating the tools. And this means in the future, there is a part of research that is very important is we need to continue working with them in order to ensure the transition between research to application. So today the first is there. Methodologies has been created. There are tools and there are demonstrators. Now there are industries that are making use of them. Many of them that I know very, very well, they are evaluating the tools. They are not in production, they are not in operation, but they are being evaluated. I suppose that there is a feedback, and the feedback will be, yes, but as Antonio mentioned before, finally, at a certain moment, so there is always a word that we need to develop in the future, that is how to ensure the transfer or the bridge from methodologies to operation. As soon as the industry validate, because if they are not confident with the result in the validation, it's very difficult to implement this in operation. So for me, when I speak about maturity, is from a certain point of view and from methodological point of view, tools for making physics, tools for speeding up physics, tools for creating models from data, tools from assimilating data, Bayesian, Kalman, all the things that we can imagine. Technologies are there, demonstrators, there are a lot, and there are many industries that are validating. Are the industries and not the operation. This is the R&D departments that are trying to discover what is the added value that this could provide in operation. And probably there is a step that is helping them for moving from methodologies to operation. But I think from the scientific point of view, today, and this is the same for any community, we need to move to generative. This was a discussion. I was invited in the Élysée Summit. Élysée, this is the summit that was organized in France by the President of the Republic about the artificial intelligence. And obviously, there is only one topic that was discussed there. The only topic that was discussed there was generative. Obviously, 90% for language, ChatGPT, 10% for science. And it's incredible. In science, people speak about climate, is science. Health, oh yes, is science. And the third one was robotic. Why robotic? Because robots speak and robots manipulate images. And images and voice or text is something that is very well known today by using LLM. Something that was strange, and I informed the CNRS in France and the minister, was technology, production, structural mechanics, planes, aircraft, all this was absolutely absent in the discussion. But one thing is clear, was generative.
Okay, thanks for your answer. I just have a question in the chat from Liam. I don't know, Liam, if you want to ask, or I can read it. Liam said that you mentioned autoencoders for dimensionality reduction.
Yeah.
Do you have experience with any other reduction techniques?
Oh, yes, I use all the reduction techniques in the history and in the war. What is the advantage of autoencoders? In general, when you are applying a PCA that is very classical, this is linear reduction, there are all the technologies about manifold learning like LLE, like KPCA, like TSNE. All this is very good. These are techniques of manifold learning. They try to learn the manifold in which the solutions are. And where we are, I will show the slide in order to explain or to respond to the question. This is an example. You can see my screen again?
Yes, yes, yes.
Imagine that you show this image. This is a small circle, another bigger circle. I show you to you. You immediately, you know that are circles. And in order to describe a circle, the only thing that you need is the radius. Radius or diameter is enough in order to describe these geometries. This for you is very nice. But imagine that you provide photos, images with plenty of pixels. Some pixels are yellow, some pixels are white, and you provide that to the computer. And the computer should understand that even when you provide 1 million of pixels, in 1 million of pixels, there is only one information, that is the radius. And so finally, this is nonlinear dimensionality reduction. And by using an autoencoder that is something very powerful, you provide circles. And at the end of the day, this guy told you, hey, guy, finally you are sending me millions of data, millions of pixels in each image. You know what? All these images there is in each one, there is only one data that is important. Obviously, the autoencoder is not explaining you that this data is called radius. And here I put an example in which, well, it's something that depends on the radius. There is only dimensionality 1. With only something that has one dimension, this means one curve, you can embed all the circles in the world. And obviously now this is fantastic for generative design, because the idea is, if I put one and I put another, now I could put many in between and I'm generating new circles. Yes, but make attention. If you are putting new, you are exploring the manifold, the nonlinear manifold, when you are in the red point, you have another circle that is in between the smallest and the biggest. But if the manifold is nonlinear, and this is always the case, or almost the case, when you put a point between the one of radius 1 and the one of radius 3, this is the red point. The red point is not in the manifold. And this means if you decode, you will obtain something that is not a perfect radius. So this is generative design. We show things, and he's providing me many other options. But you need to make attention. Autoencoder, you need something a little bit more sophisticated. That was my presentation after. And there is something that is very nice. There are rectangles, circles, triangles, pentagons, hexagons, and there is something that is very nice. There is a latent space in which the dimension is 2. Incredible. All these guys are parameterized by 2 parameters in a mathematical space, such that you can move from one to the other, and you can see something that is very natural. We are moving from a rectangle to a circle by moving in this space, and you are generating plenty of new geometries, and even more, you are generating plenty of new geometries, and in real time, I think it's in the video, in real time, you generate plenty of new geometries and the solutions. This is related to a calling process, the solutions inside. So the autoencoder, why? Because in general, we need something that is very robust with respect to the reduction. The most part of times you need something that is non-linear, and autoencoders is, for me, with all my experience working in model order reduction, the best choice as soon as you have many data. If you have no data, there are many other technologies. For example, optimal transport allows to reduce in something in which you need much less data. 3, 4, 5 is enough in order to make a generation. So this is the answer to this part.
Okay, so well, we don't have any more time for questions, but Paco already mentioned if you are interested, you can ask.
Yes, don't hesitate. Send me an email. I will respond immediately to your mail. But for personal reasons, I need to leave now. But don't hesitate. Send me an email.
Thank you very much, Paco, and I hope you have enjoyed it. But please, for the others, do not leave immediately. We have some news. Yeah, bye, Paco. Thank you.
Bye.
And we have some news, and I think Katia or Piero maybe will take the stage.
Yeah. I think I will leave the stage immediately to Piero in order to have some updates about next conference.
Yes. Thank you, Katia. Thank you, Sandrine. Paco already left. It was so I have to say thank you also to Paco for being here. You know, a lot of participants, so I can share some news, some updates about the approaching conference in PESUM. Let me share. I have some slides here, so maybe I can share my screen. Give me just a feedback if you see my presentation here.
Yeah, perfect.
Okay, perfect. So just a couple of minutes to share with you what is going on in PESUM. We are working hard, I have to say, me and also Domenico Ombrello and Luigino Fidice to organize everything. We are very excited and happy about how things are going. So it is more or less 1 month to the conference. We are refining details. And I would like to start this update just, saying thank you to all the, dynamic persons that are helping us, as members of the organizing committee. All of them are doing an amazing job, caring about different aspects. So it is not just my work here, my time. It is the work and time of an entire wonderful team that I would like to acknowledge as first thing here. So let me move here. So far, the response from the community and also non-ESA for members, I have to say, is quite good. We are happy about numbers. At the moment, we have more or less 360 registrations from seniors, students, and also people from industry and sponsors. A lot of them are from Europe, as expected, but also a good number of people will come for, let me say, far countries like Japan, India. We have several registrations from India, China, and USA also, and other countries. On this point, let me share this info. I think it is relevant for people coming from the US. Because Professor Hiab Ragai, Penn State University, contacted me since he has funding to support some mobility of students to attend the conference. So if people from the US, students mainly, are connected now, please send me an email and I will create the link in order to make everything very, very easy. So it seems that PESUM, beginning of May, is the place to be. You can just wake up in the morning, feel the sea breeze, then join the conference and enjoy the presentations and also our social program. Now, this is the plan for the 3 days of the conference. I think it is a very good plan. We will have more than 280 presentations organized in 6 parallel sessions, plus keynote lectures and also public sessions for our ISAFORM benchmarks. I have to say thank you to Anne-Maria Bracken for, giving us this input and stimulating us in, finding this time for the ISAFORM benchmark. I'm sure that they will be very interesting for people working in the field and also to give visibility to this initiative that is supported by the ISAFORM Association. And I have to say that this plan is not done by artificial intelligence. Here there is the work of two members of the organizing committee, Fausto and Romina, who worked very hard in order to prepare everything here, and also to find some time at the end of day 3 on Friday, because we are trying to understand, if possible, to close with the last coffee break and then go to visit the archaeological site, and it will be a very amazing experience. So the intention here is to have all the participants in the conference until the last moment, and then we will enjoy another moment together. And of course, please note that in day 2, there will be the General Assembly, where our president will update about the ISAFORM life and all the things that the board is doing in order to create new opportunities and so on. And I have to acknowledge also Natalie Jacobs for Springer, because she will give the workshop on how to write a good paper for our journal. So thank you, Natalie. The detailed program is on the way. It should be published. It is written soon, but most probably today it will be on the website. So stay tuned there and look for your presentation and other interesting presentations. About, the venue, it will be the Ariston Conference Center. So the board asked us to make logistics very easy, traveling smooth and so on. And we made it because on arrival on the 6th, we organized a dedicated bus transfer service from the airport in Naples to the venue. So when, after reaching the airport, look for, our buses. I will just send you some emails to the participants just to understand which is the timing of your flight. It is not my intention to disturb you, but I just want to organize everything in details. So I will contact all of you in the next weeks in order to organize everything in the best way. About the social program, the first day we will enjoy our welcome cocktail at the conference venue, around the swimming pool. And in day 2, after the General Assembly, we will move to Salerno for an amazing dinner, just looking at the wonderful Amalfi Coast and enjoying a very good food, prepared by the Michelin star level chef of the Lloyd's Bahia Hotel in Vitri. So the thing is, we will move there, and the ticket for the social dinner will be distributed during the General Assembly, so you should stay there as well. And I hope that everyone will be there. Just some other things. Okay, about accompanying person, I think this could be useful as well. We have some registrations also for accompanying persons, not huge number. So the idea is not to create a package for that, since numbers are not really high. But we are working just to prepare a list of suggestions and, support all the accompanying persons that are interested in visiting something around the venue. So check the website, because all the information will be given there. And last things, I'm trying to talk fast because, just to keep, this presentation very short. But I want to mention this initiative that we, started I mean, me and Luigino and Domenico Ombrello, so as chairs of the conference, because looking at the amount of registrations, we started thinking about, okay, we have some traveling from far countries, so flight and buses and other things, and everything will be, you know, the reason for a generation of CO2. We talked about this with some sponsors, and we started this eCO2 project, whose goal is to reach the complete CO2 compensation, so to compensate all the emissions that are coming from the conference. We made some calculations using LCA tools to understand how much CO2 we will produce during the conference, and the idea here is to plant a number of trees in order to compensate, all this emission. So coming to the conference, you will have a very good professional time, you will have a very good interaction, networking and so on. We will enjoy the place, but at the same time, I think that we are doing something good for a greener tomorrow. So I would like to steal here the usual sentence by Luca Schmeidei, because we truly believe it. ISAFORM is much more than a conference. We are doing a lot of things. So if that is what we are, our mission maybe could be summarized in these words here. What we do is to shape a better future, and we truly believe that we are doing this. And all of this is possible, of course, also thanks to our sponsors. We are receiving a lot of attention. I'm mentioning this, first of all, to say thank you to the sponsors, but also because most of them, if not all of them, will be there during the conference days, and we will to interact with the people in academy, in science, in research, to understand if there are possibilities for good cooperations and, for new developments and so on. So all these companies will be there, and we are sure that the interaction will be great. So that's it from my side. I do apologize if my presentation was a little bit too long. I tried to give pretty much all the important informations there, but in case, don't hesitate to check the website. The QR code is there, or drop an email to info@esaforum2025.it. We are reading all the emails and responding to them. In general, it is me personally replying. So in case of any doubt, contact us, and we will give you all the indications in order to make the ISAFORM 2025 an amazing experience. Thank you. That's it from my side.
Thank you, Piero. Very nice presentation, and we are really eager to go to Pestum and to visit the conference and the site, and also have an environmental responsible conference is also a very good point. So time to finish this webinar. So maybe we thank again Paco, and as a teaser, save the date, because the next webinar is already ready, and we will have in June a presentation for another very important person for ESAFORM, that is Professor Fatini from Italy. So I will leave you on this graphical abstract as a teasing for the next webinar, and I hope to see all of you in Pestum, and for sure to have you all for the next webinar. And it's time to wish you a very nice day, and to thank you for your participation to this event. Many thanks. Bye-bye.
Thank you. Bye.
Thank you.
Bye.
Goodbye. See you in a few weeks.
Yeah. It's a pleasure. Bye-bye.